Generational change is part and parcel of our lives. In terms of space exploration, the Hubble Space Telescope has been doing its extraordinary work for a generation now, and it's time to hand over the reins.
What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything.
Galileo, Herschel, Hubble. Our knowledge of space is marked by some of the greatest names in the human history of stargazing. But who was James Webb? His name is attached to the James Webb Space Telescope, which will soon be helping us understand what lies beyond even the amazing reach of Hubble. Originally called the Next Generation Space Telescope, Hubble's successor was renamed in 2002 to honor James E. Webb, who ran NASA from February 1961 to October 1968. Those dates, of course, put Webb at the heart of the American space program, and the moon landing in particular. But that was not Webb's sole preoccupation. Webb's energy encompassed robotic spacecraft, probes to Mars and Venus, and in 1965, his advocacy of a large space telescope. He was, in other words, a man of vision. The James Webb Space Telescope is nearing completion, in readiness for a scheduled launch in October 2018. By a happy coincidence, exactly 50 years since James Webb's tenure at NASA ended. Its aim is modest, to study every phase in the history of the universe. Several major agencies have collaborated in the creation of the James Webb Space Telescope. NASA's Goddard Space Flight Center is at the hub. ESA will provide the launch vehicle, the ultra-reliable Ariane 5 rocket. Canada's space agency is involved, as is the Space Telescope Science Institute, while Northrop Grumman is the chief contractor.
The Webb will be wonderful for the astronomy community. Not only will it give them the kinds of wonderful resolution we have with Hubble that you can get above the atmosphere, but it's going to bring them access to a wavelength region where many of them have not worked before.
We have a telescope that's far more powerful than anything that we have had before, working at infrared wavelengths, which you can't see well from the ground. And that will enable us to see things from the most distant universe that we can only guess at, things in the outer solar system that we can only guess at.
The Webb is going to be such a powerful telescope. It's going to be like the Hubble. And in the case of the Hubble, probably more than half of the greatest observations, discoveries that the Hubble made were things people didn't anticipate. I expect the same for the Webb.
The James Webb Space Telescope's mission duration is a planned 10 years, during which it has a number of specific goals to accomplish. It will search for the first galaxies, determine how galaxies were formed, observe the formation of stars, and measure the properties of planetary systems, both physical and chemical, including our own solar system. Not least of all, the Webb will carry on the task that underlies so much of humankind's activity in space, investigating the potential for life in other far-flung places. The 6,200 kilogram space-based element of the Webb will not orbit Earth, as Hubble has been doing. Instead, it will orbit the Sun. In line with Earth as it moves around the Sun. And that is because while the James Webb Space Telescope is looking for first light, its first task is to find darkness, the condition in which it can operate at its best. Three main component systems make up the space-based James Webb Space Telescope: an integrated science instrument model, ISM, the optical telescope element, OTE, and the spacecraft element. The key to the JWST's enhanced vision is its primary mirror, which measures 6.5 meters across. It comprises 18 segments made of beryllium, the lightest of the alkaline earth metals. A 5-layer sun shield the size of a tennis court will protect the JWST's dazzling array of specialist technology. As this orbiting infrared observatory continues the work begun by Hubble. On board are a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, a near-infrared imager, and a slitless spectrograph. The NIRSpec has micro-shutters, which will make it possible to observe up to 100 objects simultaneously. The Webb's cameras and spectrometers are capable of detecting extremely faint signals, a crucial factor in its attempt to see as far back as first light. While NASA busies itself with James Webb, its European counterpart ESA is hard at work on another related mission with a much more famous name attached to it. Euclid is named for the Alexandrian Greek whose geometrical study, the elements, formed the basis of our mathematical thinking for almost 2 millennia.
What we want is actually to continue our successful program, which is actually providing the cutting-edge space science, meeting the challenges of worldwide research.
But where the original Euclid worked only with ruler and compass, his namesake in space will have much more sophisticated instruments in its locker. Like the Webb, Euclid boasts a modest mission to map the geometry of the dark universe. Over a period of some 6 years, it will look back over the entire time in which dark energy has contributed to the accelerating expansion of the universe. Scientists tell us that what we can see accounts for less than 5% of what is there. The rest is made up of dark matter, some 20%, and the remainder of dark energy. They act in contradictory ways. Dark matter acts through gravity to play its role in forming galaxies and slowing the rate of expansion of the universe. Dark energy, on the other hand, defeats gravity and thus encourages acceleration of that expansion. The Euclid Consortium, part of ESA's Cosmic Vision program, brings together 1,000 scientists from 100 institutes in 14 countries, with added input from NASA in the United States. In 2013, Italy's Thales Alenia Space Group was named as prime contractor, with Airbus in France responsible for the payload module. On board Euclid's payload module will be a telescope 1.2 meters in diameter, a visible light camera, and a near-infrared camera and spectrometer. Euclid will undergo its critical design review in 2017, with its launch planned for December 2020 from Kourou in French Guiana. Like the JWST, it will orbit around the L2 point. Channeling the thinker whose name it bears, Euclid will be looking for genuine insight into the evolution of cosmic structures. Investigating the nature of dark energy, dark matter, and gravity, it will track their observational signatures on the geometry of the universe and on the cosmic history of structure formation. Euclid will deploy 2 key systems: weak gravitational lensing, or WL, and baryonic acoustic oscillations, BAO. WL examines how background galaxies are disturbed by foreground dark matter and measures modifications in the shape of galaxies brought on by the gravitational lensing of dark matter. BAO reveals the wiggle patterns which help us gauge the expansion of the universe, revealing the three-dimensional distribution of structures by means of the spectroscopic red shifts of galaxies and galaxy clusters. Putting it more simply, perhaps, Euclid's task, made easier by its unprecedented accuracy and stability, is to map the shape, position, and movements of 2 billion galaxies, or 1/3 of the sky. Even more excitingly, the James Webb Space Telescope is not the only star performer, pardon the pun, on the horizon. In 2016, NASA confirmed the decision to go ahead with its Wide Field Infrared Survey Telescope, or WFIRST for short.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time.
This new observatory will offer astrophysicists the best of both worlds by casting its eye both wide and deep as it seeks to shed light on dark energy, exoplanets, and cosmic acceleration. Surveying large areas in near-infrared light, a single image from WFIRST will have all the depth and sharpness to which Hubble has accustomed us, but will cover 100 times the area. In fact, a single image will encompass as many as 1 million galaxies. The new telescope's work will slip into the groove already made by Kepler, the Sloan Digital Survey, and TESS, the Transit Exoplanet Survey satellite. WFIRST will use microlensing rather than the transit method of detection. It will employ a 2.4-meter diameter telescope provided by the National Reconnaissance Office. But the best of both worlds part of the WFIRST story comes with the coronagraph, which NASA has been able to add to its instrumental array. This is a means of dimming the light from a so-called host star in order to see better the planet or planets orbiting it. And that is highly significant if we remember that the host star may be up to 1 billion times brighter than any exoplanet identified. If successful, the coronagraph technique will make it much easier to determine the chemical composition of planetary atmospheres. WFIRST will be able to use a unique deformable telescope controlled by computer. This first mission, due for launch in the mid-2020s, being what is called a technology demonstration, laying down a scientific marker for future missions to go in even more determined pursuit of life beyond the confines of our own solar system. While all of this is going on in space, Here on Earth, another agency will be tackling the question of dark matter from yet another angle. At CERN in Geneva, the Large Hadron Collider is now running at full power for the first time.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphotons. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV, and what is most important that these particles could be searched for at low energy experiment, with fixed target experiment.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
So the idea is that when the high-energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high-energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
Might its scientists be able to replicate dark matter itself?